Welcome to the deep dive. Today we're zeroing in on magnetism.
Right, a really core topic.
Yeah, and you've sent in a fascinating collection of material. It covers, well, everything from the basics, attraction, repulsion, to Earth's magnetic field, and even these clever things called electromagnets.
It's a great set of sources.
So our mission today, let's try and pull out the essential ideas from all this, make it clear, and hopefully pretty engaging too.
Sounds good. Magnetism really is, well, it's fundamental. Shapes our world in so many ways, visible and invisible.
Okay, let's unpack this. Where should we start? Maybe history.
Good idea. The sources mentioned lodestone, found way back in a place called Magnesia.
Right, lodestone, that's the natural stuff, isn't it? Like iron oxide.
Exactly. And what's really striking is that even back then, they noticed two key things. First, it pulls iron stuff towards it.
The attraction part.
Yeah. And second, it has this weird sense of direction. If you let it hang freely, it tries to point a certain way.
Ah, the compass connection.
Precisely. The sources say the Chinese were using this property, believe it or not, for navigation way back around 2500 BC.
Wow. Just think about that, using a rock to find your way. Incredible.
It really is. But as you can imagine, these natural lodestones weren't ideal.
Right, probably all lumpy and not very strong sometimes.
Exactly. Different shapes, different strengths. So eventually we figured out how to make our own magnets, artificial ones.
Like the bar magnets and horseshoe magnets we see?
Those are the classic examples. Using materials like iron, steel, shaping them properly, it gave us stronger, more reliable, more predictable magnets.
Which opened the door for, actually studying this stuff properly.
And for practical uses, too. Now, you mentioned something key earlier, that alignment.
Oh, yeah. If you hang a magnet so it can swing freely, it settles down pointing roughly north-south.
And that simple observation, that's our first huge clue about the Earth itself.
It's like the whole planet has its own magnetic thing going on. A bit tilted, maybe.
That's a great way to think of it. That consistent alignment tells us Earth acts like a giant, well, somewhat tilted magnet.
And this leads back to the basics, right? The sources remind us about poles.
Yep, the fundamental rule. Like poles repel north, pushes north away, south pushes south away.
And opposites attract.
North pole, south. That push and pull is the core magnetic force.
Okay, so we've got permanent magnets, natural and homemade. But the sources also dig into something called induced magnetism. Sounds like magnets giving temporary powers.
That's actually a perfect analogy. It's like a temporary loan of magnetic ability.
Okay.
It happens when a magnetic material, think soft iron, even some steels, gets near or touches a permanent magnet. It becomes a magnet itself, but only for a while.
Like the permanent magnet casts a temporary spell on it.
Kind of. So if you take your permanent magnet and hold it near, say, an ordinary iron nail,
Yeah.
that nail, which wasn't magnetic before, suddenly acts like one. It can pick up tiny things, like paper clips.
Ah, okay. But it's temporary, you said.
Right. And this is the really cool part. Move the original magnet away.
And the nail just drops the paper clips?
Pretty much. It loses most, if not all, of that magnetic power. The sources show this with iron filings sticking to an iron bar only when the magnets close. Remove the magnet, the filings just fall off.
So it's a fleeting effect.
Mm-hmm.
Makes sense. And this whole process, this temporary power-up, that's magnetic induction.
You've got it. That's the term.
Yeah.
And there's a specific way the power is induced. The polarity.
Polarity.
North and south poles.
Exactly. The end of the nail, or whatever material it is that's closest to the permanent magnet, it gets the opposite pole.
Wait, opposite. So if I bring a north pole near it?
The end closest to your north pole becomes a south pole, and the far end of the nail becomes a north pole.
Huh. Seems a bit backward, but okay.
It's how the magnetic forces line up. And this leads to a really important idea the sources mention. Induction precedes attraction, meaning the iron piece first becomes a temporary magnet through induction. Then the attraction happens because you've now got opposite poles facing each other.
Ah, I see. The induction has to happen before the pole.
Precisely. Think about making a chain of iron nails hanging from a magnet. Each nail induces magnetism in the next one down the line. That's how the chain holds.
But if I take the main magnet away...
The induction stops, the temporary magnetism vanishes, and the whole chain just falls apart.
Okay, that clicks. Induction first, then attraction. So magnets interact, they can temporarily influence stuff. Now, what about this magnetic field the sources keep talking about? An invisible force field.
That's pretty much it. The magnetic field is this region, this space around a magnet where its magnetic influence can be felt.
How do we know it's there?
Well, the classic way is with a compass. If you put a compass needle inside that field, it won't just point to geographic north like usual. It'll feel the magnet's force and swing around to align itself differently.
So if I walked around a bar magnet holding a compass, the needle would keep changing direction.
Constantly. It would always try to point towards the nearer pole of the magnet. The direction it points shows the direction of the magnetic force right at that spot.
And presumably, the further away I get.
The weaker the influence.
Yeah.
Exactly. The field strength decreases with distance, like sound fading as you move away from a speaker.
The sources also call the magnetic field a vector quantity. Sounds technical. What's that mean practically?
Just means it has two key bits of information at every point. Strength or magnitude.
How strong the push or pull is.
Right. And direction.
Which way the compass needle points.
Exactly. Strength and direction, that's what makes it a vector.
Okay. Now, I remember seeing those cool patterns, sprinkling iron filings on paper over a magnet. They make these curves.
Ah, yes. That's a fantastic way to actually see the shape of the invisible field.
How does that work?
Those tiny iron filings, when you sprinkle them, they each become tiny temporary magnets themselves through induction.
Ah, induction again.
Yep. And then, like tiny compass needles, they line themselves up along the pathways of the magnetic field. They trace out the field lines, makes the invisible visible.
So each curve is a magnetic field line.
That's the idea. It's a continuous curve, and the tangent, like a tiny straight line just touching the curve at any point, tells you the exact direction of the magnetic field right there.
Okay, so they're like a map of the field.
Yeah.
What are the rules for these map lines, their properties?
Good question. There are several key ones. First, they always form closed loops. They come out of the North Pole,
Right.
curve around through the air to enter the South Pole.
Okay.
But they don't stop there. Inside the magnet, they travel from the South Pole back to the North Pole to complete the loop.
So they're continuous, no beginning or end.
Exactly.
Yeah.
Second, outside the magnet, the direction is always shown going from north to south. That's the convention.
North to south, outside. Got it.
Third, the tangent rule we just talked about always shows the field direction. Fourth, and this is crucial, magnetic field lines never cross each other.
Never. Why is that so important?
Think about it. If two lines crossed at a point, what would a compass needle placed right there do?
It would have to point in two directions at once.
Which is impossible. The magnetic force at any single point can only have one direction. So no crossing lines.
Makes perfect sense. What else?
Well, how close together the lines are tells you about the field's strength. Where they're crowded, like near the poles.
Stronger field.
Right. Where they spread out, like further away or near the middle of the magnet.
Bigger field.
Exactly. Also, if you see lines that are parallel and equally spaced, that represents a uniform magnetic field. Same strength, same direction everywhere in that little region.
Like Earth's field over a small area, maybe?
Precisely. Earth's field locally can be considered uniform. And finally, a sort of conceptual point. They behave a bit like stretched elastic bands. They try to shorten explaining attraction and push each other apart sideways, explaining repulsion.
Okay, wow. Lots of rules for invisible lines. So let's zoom out now. Earth's magnetic field. We know a compass points north. What other proof do we have that our planet is a giant magnet?
The sources list some compelling evidence. The compass is the big one, obviously. A free magnet aligns north-south.
Check. What else?
This is fascinating. If you bury a plain iron rod in the ground pointing north-south and leave it there for a long time, it actually becomes a weak magnet itself.
No way. Just from sitting in the ground.
Yep. It gets slowly magnetized by the Earth's field. That wouldn't happen unless the Earth had a field.
Okay, that's pretty convincing. Any other evidence?
Yes, the existence of neutral points. We'll probably talk more about those. But they are spots near a bar magnet where its field and Earth's field cancel each other out.
A magnetic dead spot.
Sort of. A compass there won't know which way to point. These spots only exist because Earth has its own field interacting with the bar magnet's field.
Interesting. Cancellation implies two forces.
Exactly. And the final piece is the angle of dip. If you have a compass needle that can tilt up and down, not just side to side,
Okay.
it won't always stay horizontal. The angle it makes with the horizontal changes depending on where you are on Earth.
So it dips down or points up?
Right. Near the Earth's magnetic poles, it points almost straight down or up. Near the magnetic equator, it's horizontal. This global variation maps out the structure of Earth's field.
So Earth has magnetic poles just like a bar magnet.
It does, but here's a twist. They don't line up perfectly with the geographic north and south poles, the ones on our maps, related to the spin axis.
A far offset.
Yeah, by about 17 degrees, according to the sources. the Earth's magnetic axis is tilted relative to its rotation axis.
So wait, when my compass points north.
It's actually pointing towards Earth's magnetic south pole, which happens to be located up near the geographic North Pole, currently in Arctic Canada.
Whoa, okay, so magnetic south is near geographic north.
Correct. And conversely, Earth's magnetic North Pole is down near the geographic South Pole. And get this, these magnetic poles aren't fixed. They wander over time.
That complicates things. So near the surface, what do these Earth field lines look like, say, in this room?
Locally, in a limited space, we can approximate them as being parallel, equally spaced.
Uniform.
Right, uniform. And directed generally from geographic south towards geographic north, horizontal near the magnetic equator, more vertical near the poles. You could actually plot them crudely with a compass.
Okay. And you mentioned neutral points again, where the fields cancel out.
Exactly. When you put a bar magnet down, its field interacts with the Earth's field. A neutral point is where the bar magnet's field is exactly equal in strength, but opposite in direction to the Earth's horizontal magnetic field component.
So they fight to a standstill. Net field is 0.
Precisely 0. So a compass needle placed right there has no preferred direction. It just sits there confused.
And where do these spots show up? Does it depend on the magnet's orientation?
Absolutely. If you place the bar magnet so its north pole points towards geographic north,
Okay.
you'll find 2 neutral points, one on the east side, one on the west, equidistant from the magnet center.
East and west. What if I flip the magnet? South pole pointing north?
Then the neutral points shift. They'll still be equidistant from the center, but now they'll be located on the north and south sides of the magnet along its axis.
Interesting. And the overall field pattern would show the magnet's strong curved lines close up, blending into Earth's more parallel lines further out.
It's exactly what you'd see if you mapped it with iron filings or a compass. Strong local field dominates near the magnet, weaker Earth field takes over further away.
The sources even show this, and mention an example with a horseshoe magnet making needles attract each other, induced magnetism again. Plus, lots of questions to check understanding.
Yeah, those examples really help connect the concepts.
Oh.
Okay, so that covers natural magnetism and Earth's field pretty well. Shall we move on to how we make magnets using electricity, electromagnets?
Yes, let's do that. So an electromagnet, the sources define it as a temporary magnet, right? But often a really strong one.
That's the key. Temporary, but potentially very powerful. And it's made by sending an electric current through a wire coiled around a soft iron core. Magnetism on demand.
Turn on the power, you get a magnet, turn it off, it stops.
Pretty much. And they usually come in 2 main shapes. A straight bar, the I shape.
Like a regular bar magnet.
Yep. And the U shape, like a horseshoe magnet.
Okay, let's start with the straight one, the I shape. How's that built?
You take a straight bar of soft iron, and you wind insulated copper wire around it tightly. That coil of wire has a name, a solenoid.
Solenoid, okay.
Then you hook up the ends of that wire to a circuit. You need a power source, usually a battery for DC.
DC, direct current.
Right. An ammeter to see how much current. Maybe a rheostat that's like a dimmer switch to control the current. And crucially, a switch to turn it on and off.
Got it. So what happens when I flip that switch?
Current flows through the core, and bang, it creates a magnetic field. The soft iron core inside the coil gets strongly magnetized.
And it gets poles, a north and a south.
It does. And which depends on which way the current is flowing in the coil. There's a rule for that.
Oh yeah, the sources mentioned a clock rule.
That's the one. If you look at one end of the coil, and the current seems to be flowing clockwise.
Clockwise?
That end becomes the south pole. If it looks counterclockwise.
That's the North Pole.
Exactly. And because it's soft iron, it doesn't hold on to magnetism well. Its retentivity is low.
Retentivity, like magnetic memory.
Good way to put it.
Wow.
Low memory.
Yeah.
So as soon as you switch the current off, poof, the magnetism mostly disappears. Very temporary.
Useful for things that need to switch on and off, I guess. The sources mention relays.
Yep, relays are a classic example using an electromagnet to flip a mechanical switch in another circuit.
Okay, now the U shape, the horseshoe one. How's that different?
You start with a U-shaped piece of soft iron. You still wind coils on it, but you wind them on the 2 arms.
Yeah.
And here's the clever bit. You wind the wire in opposite directions on the 2 arms.
Opposite. So if one is clockwise.
The other is wound counterclockwise when viewed from the ends.
Why do that?
When the current flows, this opposite winding creates opposite poles right next to each other at the ends of the U.
Ah, so you get a north pole on one tip and a south pole on the other, facing each other across the gap.
Exactly. And this setup concentrates a very strong magnetic field in that gap between the poles.
Stronger than the straight bar type?
Generally, yes. especially in that gap. And like the I shape, it's temporary because of the soft iron. You find these in things like electric motors, generators.
Right. And the sources emphasize using DC, direct current, from a battery for a steady magnet.
Yes, because if you used AC, alternating current,
The current flips back and forth.
so the magnet's polarity would flip back and forth constantly, really fast, which might be useful sometimes, but not if you need a steady north and south pole.
Okay. Now, if I want a really strong electromagnet, what can I do? How do I boost its power?
Two main ways, according to the sources. First, increase the number of turns of wire in your coil. More loops equals more magnetic effect adding up.
More turns. Simple enough.
Second, increase the electric current flowing through the wire. More current means a stronger magnetic field generated by the wire itself, which then magnetizes the core more strongly.
More turns, more current. Got it. So these are temporary, controllable magnets. What about the permanent kind? How do we make strong, permanent magnets?
For those, you typically start with a material that does have good magnetic memory, high retentivity. Steel is the classic example, much better than soft iron for holding magnetism.
So use steel instead of soft iron?
Right. And the process is often similar. Initially, you place the steel inside a very strong magnetic field, usually generated by a powerful electromagnet, a big coil with lots of current.
You blast it with magnetism.
Essentially, yes. You align all the magnetic domains inside the steel. And because steel has high retentivity, once you turn off the external field, the steel keeps a lot of that magnetism. It becomes a permanent magnet.
And these are used in things like compasses, meters.
Exactly. Where you need a reliable, constant magnetic field without needing electricity.
The sources have that useful table comparing them side by side, right? Electromagnets versus permanent magnets.
Yeah, it lays it out clearly. Soft iron versus steel, temporary versus permanent, strength adjustable versus fixed, potentially very strong versus not usually as strong, polarity reversible versus fixed, easy to demagnetize versus hard. It's a great summary.
And those differences really highlight the advantages of electromagnets for certain jobs. What are the big wins for using an electromagnet?
Well, number one is often sheer strength. You can make electromagnets way stronger than almost any permanent magnet.
Brute force.
Yep. Second, control. You can dial the strength up or down just by changing the current.
Adjustable power.
And third, you can flip the poles, make north-south and south-north just by reversing the direction of the current flow. Try doing that with a permanent magnet.
Right, impossible. So strength, adjustability, reversibility. Makes sense. Where do we see these advantages put to use? The sources listed quite a few examples.
Oh, tons. Huge ones for lifting scrap metal, girders, heavy iron stuff. They can lift thousands of kilograms.
And then just drop it by switching off the power.
Exactly. Loading furnaces, separating iron from other junk in mines or recycling plants.
Useful.
Even delicate things,
Yeah.
like surgeons using tiny electromagnets to remove iron splinters from an eye or wound.
Wow. And in science labs.
Crucial for research, studying how materials behave in strong magnetic fields. And then there's all the electrical devices.
Right, the list was long. Electric bells, telegraphs, motors, relays.
Microphones, loudspeakers. They're hidden inside so much of our technology.
Let's zoom in on one of those, the electric bell. Classic example, right? How does that little thing work using an electromagnet?
It's a really neat mechanism. Usually uses a U-shaped electromagnet with that soft iron core.
Okay, the horseshoe type.
Then there's a little piece of soft iron called the armature. It's mounted on a springy metal strip, and attached to the armature is a little hammer.
The hammer that hits the gong.
That's the one. The hammer sits near the gong. There's also an adjusting screw that acts as an electrical contact point touching the springy strip. And of course, a switch and a battery.
So how is it wired up?
The circuit goes from the battery, through the switch, through the coil of the electromagnet, and then through that contact point between the adjusting screw and the springy strip, and back to the battery.
Okay, so pressing the switch completes the circuit. What happens then?
Current flows through the electromagnet's coil. It instantly becomes magnetic.
And pulls the armature towards it.
Exactly. It attracts the soft iron armature. As the armature moves, the hammer attached to it swings over and hits the gong. Ding!
There's the ring. But what else happens when the armature moves?
Ah, here's the clever part. As the armature moves towards the magnet, it pulls the springy strip away from that adjusting screw contact point.
It breaks the circuit.
Precisely. The electrical contact is broken, the current stops flowing to the electromagnet.
So the magnet switches off.
Instantly. It loses its magnetism, now that it's not pulling the armature anymore.
The springy strip pulls it back.
Right. The spring pulls the armature back to its original position.
Yeah.
And when it does that, the strip touches the contact screw again.
And the circuit is complete again.
And the whole cycle starts over. Electromagnet turns on, pulls the armature, hammer hits gong, circuit breaks, magnet turns off, spring pulls back, circuit remakes.
And it just keeps doing that really fast as long as I hold the button down, making it ring continuously.
That's exactly it. A self-interrupting circuit driven by the electromagnet. Brilliant little piece of engineering.
It really is. And the sources note that even AC can make it ring because the attraction happens regardless of which pole is which.
Yeah, the armature is just attracted to the magnetized iron core. Doesn't care if it's a north or south pole facing it. So the rapid flipping with AC still makes it vibrate and ring.
Fascinating. And again, more examples and exercises in the source material focusing just on these electromagnets and bells.
Helps solidify how it all works.
It's truly amazing, isn't it? How these principles, from Earth's own field down to these man-made devices, are all connected through magnetism.
Absolutely. We've covered quite a bit today. Induced magnetism, fields and their lines, Earth's magnetism, those neutral points, how electromagnets are built and work, their pros and cons, their uses, and that neat electric bell example.
Understanding these core ideas really does give you a different perspective on, well, everything from compasses to scrapyard cranes.
It really does. It's
Oh.
fundamental physics with very tangible applications.
So, as we wrap up this deep dive on magnetism, here's something for you, our listener, to think about. We heard Earth's magnetic poles are wandering. How might navigation tech need to change in the future to cope with that?
Good question. Or thinking about induced magnetism, that temporary effect. Are there completely new ways we could use that? Maybe in material science or computing, things we haven't even thought of yet.
Definitely some magnetic ideas to ponder. Thanks for diving deep with us.